for joining. Okay, thank you very much for joining the second day of this seasonal school. So, we'd like to start the first session of this day. So, we'd like to welcome Professor Kyu Jin Cho from the Seoul National University. So, at first, I'd like to introduce the Cho Sensei. So Professor Cho is a professor and the director of Soft Robotics Research Center and Biorobotics Laboratory at Seoul National University. So he received his PhD in mechanical engineering from MIT and his bachelor and master from Seoul National University. So he was a postdoctoral fellow at Harvard Microrobotics Laboratory before joining Seoul National University in 2008. So he has been exploring novel soft bio-inspired robot designs, including a water jumping robot, origami-inspired robots, and a soft wearable robot for the heart called X-Glow. He has received the IEEE LAS Early Academic Career Award for his fundamental contribution to soft robots and biologically inspired robot design. And he has also many awards. So he is a very expert of this research area. So I'm very happy to welcome Kyu Jin Cho. And the title of his talk is the Tendon Driven for Soft Wearable Robots. Okay, Cho Sensei, please share your screen and please start your presentation.
Okay, thank you very much for the introduction. So today I'll be talking about tendon drive for software robots. I don't think I ever gave a talk in this topic because always the tendon drive was sort of an accessory for our software robots, but it's my great pleasure to give you a talk about our tendon drive itself. So as many of you might already know, our lab has been developing a exoglove since around 2009, almost for 10 years now, and we've been developing several other prototypes and several different types. And all these exogloves are based on tendon drive. So if you might recall, back in like 2009, there was no word, even soft wearable robot was not there. And there was no like tendon-driven soft wearable hand at all. So, but we decided to develop this kind of tendon-driven soft wearable robot because if we thought that if you use rigid frames, it becomes bulky. Instead of using rigid frames, you could choose to use pneumatics, but pneumatics is still bulky for the hand because hand, as you can see, has so many large degrees of freedom in a compact area. So we decided to go for a tendon-driven based soft wearable robotic hand called Exoglove. Started with something that can be driven with 3 fingers. It was fabric-based, 1 motor for the thumb and 1 motor for the index and middle, and it's under-actuated. So this was our unique property. Our soft wearable hand was under-actuated. There are many under-actuated robotic hands, but being able to do under-actuation for soft wearable robot, I think it's an important feature. And also we developed what's called a dual slag enabling actuator, which I'll be talking about later. So this is the concept of under-actuation, as you might already know. Many people have been developing under-actuation mechanism, mostly based on moving pulley or this kind of linkage mechanisms. But if you try to use this in the hand itself, it'll be pretty bulky. And we wanted to use under-actuation because if you use pneumatics, it's intrinsically under-actuated. But if you do tendon drive, you will need, if you don't have an under-actuated mechanism, you'll have to drive each finger separately. So we wanted to reduce the number of motors as much as possible. So that's why we came up with this under-actuated mechanism. It's published in RAM back in 2015. And we called it soft tendon routing system. And this soft tendon routing system includes slag enabling actuator plus this kind of under actuated mechanism. If you use this under actuated mechanism, even with a single motor, if you block this finger, the other finger will keep on moving. So we applied that tendon drive into our exo glove, and we were able to show that with this glove, SCI patient can actually use his hand again. And because we are using under actuation, he can use it to grasp many different objects without using a complicated control. And with 50 newtons of tension, we could generate a pinching force of about 20 newtons and wrap grasping force of about 40 newtons. And maximum grabbable object size was about 76 millimeters in diameter. And then after that, we developed what's called exoglove poly. So from fabric, we went to polymer, so changed our base material because of the hygiene issue. People were telling us that if you use fabric, there's hygiene issue. So we developed this polymer-based exoglove poly. And for the thumb, we thought even if this is a passive thumb, this can be actually quite useful. And we could reduce the cost by reducing the number of motors. So we made it just single motor, under actuated, again, dual select enabling actuator, which is pretty similar to linear actuation system. And these two are the key technical features. So this video is showing the under actuation mechanism. So as you can see, if you grab this finger, the other finger still moves, right? So, and if there's nothing blocking, these two fingers move together. So if whatever the object shape is, you can actually grab it with this under actuation. And this is the concept of dual select enabling actuator. As you can see two tendons in different direction. And what you can see is these tendons, they keep on working even though there is no tension in this area. And there's a slack in this part. I think this is a very important feature because if you want to have this kind of feature, you have to either use a linear actuator, which is quite bulky because it has ball screw. If you use just pulley, then things are going to get tangled. So we've published 2 papers about this tendon drive actuator, one in 2017, another last year. So one paper is called Novel Slag Enabling Tendon Drive that improves efficiency, size, and safety in soft wearable robots. And another recent one is called Slider Tendon Linear Actuator with under actuation and fast connection for soft wearable robots. So this presentation is based on those 2 papers. So conventional tendon-driven robots, as you can see, this kind of tendon-driven robots, they all have tension on antagonistic tendon. It prevents derailment. Also, it increases the response time as well. So rigid structure supports bidirectional tension. And because you use bearings, there's relatively low friction. So even though there's tension, it's okay. And for rigid robots, derailment problems do not occur. But move that to soft robot with tendon drive system. If you apply tension on the antagonistic tendon, there's a problem because there's unintended movement due to pretension, and also derailment can occur. Also, friction could be really high. So if you use the same tendon drive as the rigid robots for your soft wearable robot, you're gonna have all these kind of problems because of the tension that's inside the tendon. So this video actually shows us a actuation of soft robot with and without pretension. So above one, there is a pretension on the antagonistic side. So if there's this kind of pretension, you can see that if there's a pretension on the flexor side, extension does not work well. So you want to remove that tension. You don't want like antagonistic tension on both sides. So this is what we developed, and we call it a slag enabling actuator. So you know that slag, it's not good, right? If you have slag, it means that it's going to get all tangled, but this actuator enables slag. So that's why we call it slag enabling actuator. And if you look at this side, there is no derailment at all. There is no derailment, and additional structure pulls the wire when the spool unwinds. And with this kind of process, there is no wire stranding problem. So this is the details of slag enabling mechanism. So basically what happens is you have a one-way clutch that makes the feeder to rotate without considering the gear connection. And for the unwinding process, feeder pulls the tendon faster than the spool linear speed. And so this is another slag enabling actuator. It's a different type from this one. It's called a slider tendon linear actuator. So in this actuator, what we did was we located the under actuation mechanism to the actuator instead of the hand. So the friction and complexity issues can also be solved. And we call this slider tendon linear actuator because, as you can see, there is a slider on top of the motor, and then there is this spring. So novel actuator that contains under actuation mechanism has been already developed. So this is a tendon-driven linear actuator. So basically, you can replace the linear actuator with this. So this is much more compact, much more lightweight, but you can use it instead of the ball screw type linear actuator. So as you can see, this is the wire that goes to the wearable hand, and tendon-driven linear actuator is advantageous because it's compact in size. It's better for impact because there is a compliance. And but the problem is it can only generate pulling force. So like actual linear actuators you can push and pull, right? Because there's a ball screw. But this one, you can only pull. But actually that's not a problem because our tendon drive only pulls. You cannot pull. I mean, you cannot push a tendon, right? So that means that there is no need to use the ball screw type linear actuator. But many people still use ball screw type linear actuator, especially when you're like testing. When you're testing your setup, because it's okay to have big actuators. But as you can see, if you use our tendon-driven slider tendon linear actuator, you don't need a linear actuator. So you're showing that this kind of entanglement can occur, but if you use our slider tendon linear actuator, there is no entanglement. There's the spring. And another positive side of this is that you can reduce the actuator size because you can actually double the stroke by using multiple pulleys. And so here you can put like multiple pulleys and you can do a stroke amplification. So if you use by X, you can multiply by 4. So with a small form factor, you can generate large displacement. So this is the actuator length, this is the actuator cross-section area, and this is the actuator volume. And you can locate the mechanism at the actuator for the usability. So like I said, instead of having it's good to have an under-actuated linear drive, because if you have this kind of under-actuated mechanism, you can have your hand grasp many different things without complicated control. So as you can see here, we place a under-actuation mechanism here. So here we are showing a under-actuation mechanism. This is how we show the under-actuation mechanism. There's 2 tendons connected to 1 motor. So this pulley actually pulls these 2 sets of pulleys. So when there is no external force on either, or if there is an even external force, these 2 actuators move together. But if there is only one force on the one actuation force on just single tendon, other tendon keeps on moving, which means it will adapt to the shape. So this is the positive side. And as you can see, if you have the under actuation mechanism inside the glove, there's friction. But if you put the underextension mechanism on the actuator side, simple tendon routing, it's possible to add other functions, and it's low friction because we are using bearings. So this is our slider tendon linear actuator. And another feature that I didn't show here is one very positive feature. It's not in this slide. Is it's detachable, meaning this whole thing can come out. So if you're using a tendon drive, your motor is connected with a sheath, right? You have a transmission sheath which is connected all the way to the robot. And you cannot detach this because tendon has to be connected all the way through. But for this actuator, we have this portion can be taken out. This whole set can be taken out. So the motor and the tendon part can be separated. So we are planning to actually provide this to the research community. We are preparing right now to actually make this available. We'll try to produce this in numbers of 10s, 20s, and we're planning to set up a website to provide this to the research community, because I think this actuator can be very useful for people doing research in soft wearable robots. From here, I'd like to show you some other examples of soft wearable robot that's driven with this soft tendon. So this is called ExoWrist for CIMT. So ExoWrist is a soft tendon driven wrist wearable robot with active anchor for dart throwing motion in hemiplegic patients. This was published in RAL in 2019. So we wanted to do wrist assistance because wrist is a multi-DOF joint which plays major role in manipulation. However, current wrist robots focus on multi-DOF, so it's complex and bulky, and it's not adequate for performing daily activities or task-oriented therapy. So our ExoWrist is simple, but it's effective 1 degree of freedom wrist assistive device. It's for assistance of tasks during daily living. And this is cable-driven, tendon-driven, and assists radial extension motion. So 2 main features is one, that it can do dart throwing motion. So this is the dart throwing motion. Because dart throwing motion is the motion that is widely used with your wrist. It has an active forearm anchor. And we wanted to use this for constraint induced movement therapy. Some people might already know what CIMT is, but constraint induced movement therapy is you force to use the affected side by restraining the unaffected side of your hand. So if your left hand, for this kid, your left hand is the affected side, your right hand is unaffected. So you actually fix that. And then you don't use your normal hand, and you only use your affected hand. It's intensive therapy. It's task oriented. So it's assumed to be a good way of training your hand. And the problem is that there are a large number of patients who cannot perform the CIMT because they cannot move their wrist. So if they can move their wrist, they can perform this kind of CIMT therapy. So 2 key features. One is that, like I said, we have a customized tendon path and a wrist ring, which allows to perform this dart throwing motion. The second is we wanted to develop an active forearm anchor. Active forearm anchor means that if you have pressure on your arm all the time, then it's going to be very uncomfortable. So you want to have this kind of anchoring only when you are performing this movement. So as you can see from this video, we have developed an active anchor. It's like a garment. So we have several bearings. And if you pull this tendon, actually what happens is you actually compress. So after you compress your anchor, now you can move your wrist. So if you don't compress your anchor, the wrist doesn't move. So we figured that this kind of active anchoring enables patients to use this device for a long time. You want the patients, you want to is able to use this device for a longer time as much as possible. But if it's uncomfortable, you're not going to use it. So this is the feature of this device. So we've done experiments. So moving assistance experiments showed this kind of measured and desired movements. Also experiment 2, it's the active forearm anchor. It's the main concept is anchor can turn on and off. So depending on the situation, it can prevent pressure issues and increase user satisfactory. It has 3-layer structure, and it has a moving pulley-based wire mechanism. So even with a small torque, you can do this. You can actually perform this kind of active anchoring. So the structure is pretty compact. And this is the active forearm anchor experimental results. So you can see that for different pressures, you can see how much the tension versus the displacement changes. So you can see that 15 newtons of force can be resisted with a neutral position. And the third experiment was torque assistance. And what we did here was we instructed the subject to rest in the initial position on the zig and hold the pulling rod after wearing the robot. And then we commanded each participant to exert their maximum wrist extension force in 5 seconds. And then 3 kinds of 18 trials, and then 30 seconds break between the trials. And each trial robot was in one of 3 different states, and the order is randomized. So this was the result that we got. We saw this kind of a torque of around 1 Newton meter, pretty high torque assistance when activated. So versus non-activated, we could get more than 10 times higher torque. And another of our recent work back in 2019 is development of intention detection method that predicts actuation timing from user behaviors. This was published in Science Robotics back in 2019. And the title was Eyes Are Faster Than Hands. A soft-wearable robot learns user intention from the egocentric view. And this is basically an intention detection method that can adapt to all different kind of hands. And this was done in collaboration with a KAIST professor, Professor Song Cho, who is an expert in AI. So our issue for our soft-wearable hand was, how do you detect the intention? Of course, you can do biosignal, and I know this area is growing bigger and bigger, and hopefully we will have these kind of devices that can actually detect one's intention. Maybe you can use EEG, EMG, and those kind of things. But for our exoglove, we started with a mechanical switch, because the reason that we used mechanical switch was the user actually preferred to use this kind of simple mechanical switch instead of using his biosignal. He said using biosignal, it's complicated. So I think it's a preference, but we use the mechanical signal. And for issue of using biosignal, of course, you need to calibrate every time. You need, if you use mechanical switch, you need additional actions. You're limited to single output or maybe 2. So to increase the usability, we have to actually be able to do natural motion and also various intentions. So our hypothesis was that your arm behavior and the relationship of your arm with your hand and the object interaction, there is the intention. So you can predict your intention by observing the arm behavior and the hand-object interaction. So we called it VideoNet. This is the proposed method. So what we did was we had this SCI patient attach a camera on his head, So it's like a Google Glass, and it's a first-person view. And this is a vision-based intention detection network. And you have this dual slag enabling actuator with the exoglove pulley. So again, this is under-actuated. So all we needed to find out was, instead of using this kind of like one user commanded button, our method predicts the user intention from this arm behavior, and then also this hand object interaction. And this camera observes these two, and by observing these two, it can detect the intention of the person and actually allow a disabled person to grasp those things. I'm not going to talk in detail about this algorithm. Basically, the structure is made of CNN and RRN with a spatial layer and temporal layer. And we did labeling of these data sets. We didn't do a lot. We had a single object, a red bottle, and we had a total of 26 videos. And we trained the validation 8 to 1-to-1, and only labeled intentions were rest, grasping, and releasing. There wasn't any other object-related labels or any other labels. And we verified the intention by looking at the EMG. We compared the EMG with the VideoNet. And we found that it's slightly faster. So it means that it actually predicts the intention. It's not detecting the intention, but it's predicting the intention. So we were curious how the machine learning is interpreting this VideoNet. So we did a few experiments. For example, this is the experimental setup. We had the reference block, we had the linear guide, IR sensor, distance sensor, and then we actually measured the distance, and then we showed that the relationship between these. So this is the subjects grasping various objects. So the subject was, this is the red bottle, that was the learned object. So this was the only learning that was done. And then we use it for many different unlearned objects, and we show that it can be used for all these objects. This is because the glove is using slag enabling actuator together with a under actuation. So we show like this kind of things can be possible. Other recent work is our exoglove power. So this exoglove power actually also uses a slag enabling actuator, and it has a single EMG sensor based control. So what we found was, probably you know that people use multiple 6 or 8 EMG sensors around the arm to detect the intention. So you can detect whether the person is trying to do rock, paper, scissors and those kind of things. But what we did here was we used only single EMG. One EMG placed on the muscular tendinous junction. So this is the MTJ. This is the junction between the muscle and the tendon. And we found that if you attach EMG there, you could actually get a pretty clear signal about power grasp. And because power grasp is a very useful grasp, even just with a power grasp, you can use it for many different applications. So we developed this exoglove power, which is a compact and portable tendon-driven soft robotic glove, and augments the grasping force while the user intends a firm power grasp to secure the object. And we thought it could assist firefighters, first responders, astronauts who, just like the GM NASA glove. And we were decoding the user's power grasp intention with the EMG. So as you can see in this video, this is a single EMG. It's repetitive grasping for 10 seconds. So this person is wearing the exoglove power. And what he's doing is he's actually grasping, releasing, and he's repeating that. And you can see that the red light, right? We did like 20 more trials, and we believe having this kind of glove for these kind of first responders who need to wear this kind of thick glove. They need to wear this thick glove, and which makes their hand hard to use. So this kind of exoglove power can help these kind of people. And because the control is also pretty simple, I think it's very practical. It's very practical in terms of the actuator hardware, slag enabling actuator, plus these single EMG sensor. So we published it in IEEE Transactions on Medical Robotics and Bionics. Actually, it's not under revision. It's been published early this year. So it's a single EMG sensor-driven robotic glove control for reliable augmentation of power grasping. So if you're interested, you can look up this paper and read it more. So this is the experimental evaluation of the results. So what we did was we prepared the experimental setup, the 8 participants, 3 arm postures, 6 hand and each participant performed 3 arm postures, 6 hand and wrist motion. And as you can see, this is the training set with this arm posture. And the test set is composed of 3 different arm postures. This 90 degrees arm posture, this straight arm posture, straight down arm posture. And these are 1, 2, 3, 4, 5, 6 different types of hand motions. And the results that you see here is despite the person is at a different arm posture. So people, I know if you're using EMG, you will see that EMG signals changes with the arm posture. So you will have to calibrate your signal based on the arm posture or do a machine learning, including all the data sets together with all different arm postures. But for our case, we only trained it with a single arm posture for 6 different hand motions. And myoelectric signal bursts only when performing high force power grasp. So yes, so this is one of our most recent result on self-tendon drive. So yeah, thank you very much. So if you have any questions, please let me know.
Okay, thank you very much for your very, very interesting talk. So there are several questions. So firstly, Mattia Franti Carini. No. Sorry, I cannot pronounce. Okay, the next one is Emia Bobe. Sorry, Emia.
Sorry, I didn't activate the audio.
Okay.
I was talking myself alone.
Okay,
sorry.
Later I will ask them. Okay.
Okay. No, I wanted to thank you for the presentation, which I found very interesting. And I was wondering about the exo wrist in particular for the CIMT application, because you said that you were using as a trigger for the activation in general for your work, the VideoNet approach. So I was wondering, since you wanted to use the affected end and you want to do some rehabilitation and not only assistance, how do you make the assistance? Because in the rehabilitation field in general, they use some trigger only to help the patient achieve the entire movement in order to activate the neuroplasticity of the brain. So I was wondering if you can think of the VideoNet as feasible for the rehabilitation approach.
Yes, thank you for the nice question, wonderful question. So we haven't gone up to that level with the ExoWrist. So with ExoWrist, we haven't actually applied it to a CI. We were targeting CIMT, but we weren't able to perform experiments with the actual patients. We only developed the device. But like you said, you can use the video net for intention detection of the motion, and or like you said, we can use the video net, or we could use other means of the intention detection. And our contribution in this exercise side was more focused on creating this darting motion, and with this active wrist anchor. So we aren't working on CIMT. If you're interested, we can work on that with us.
Yeah. I work at the moment at a neuropsychiatric environment, so for children. So it will be very interesting, I think.
Really, I see.
Yeah. Thank you for your answer.
All right, thank you.
Okay, thank you very much. So next is Emil.
Thank you very much for your presentation. I was wondering about the cable slack mechanism that you presented. I think it was a one-way clutch, kind of, in the beginning of the presentation. Just as far as I remember, there was a kind of gear mechanism. So did you face with the force discontinuity? Of course, it's related to the frequency and the moment smoothness, but what I see is, maybe, I'm not sure, but for the fast movement, there could be some discontinuity. I don't know.
So actually, this feeder, this feeder rotates a little bit faster than the spool. So actually, there's a slippage. So there's no discontinuity, but the problem would be actually the friction between this feeder and this. So this one-way clutch is on the feeder, and there is a friction that occurs, and that friction actually could frail the wires, depending on which wire and which pulley you're using. But we found a solution for that. But for discontinuity, maybe you mean like
I didn't
hysteresis, or
I didn't use the correct word, like maybe some fluctuations in the force output during the transmission or something.
So actually there could be some hysteresis, and also there could be some non-linearities, including discontinuity. But because our application, it's not like precision, robotic hand, it's for assisting human hand, which is pretty rough, I would say, which doesn't really require as of now. As of now, we don't need precise control, because there is no good device that can do even just rough control. So maybe later, if the technology becomes more developed, then people might start looking into the hysteresis. That's what they do with the surgical robot like tendon drives. People look into the nonlinearities and hysteresis. So actually, we've also looked into those kinds of hysteresis for the tendon drives. And we published a paper about the reliability of the tendon sheath. I forgot to include that here, which was published in IJRR 2 years ago. Reliability of the tendon drive. So if you look at that paper, we have all those like more detailed evaluation about those hysteresis. And we also published a paper about using a BOA sensor. BOA sensor is we can put a sensor inside the sheath. So if you put a sensor inside the sheath, you can actually do a feed-forward control of the tendon drive. So I didn't put that much detail in here, but if you look for our paper on the BOA cable, we called it the BOA, BOA. We actually we can actually let me see if I can pull out that.
Yeah, can you will you share the papers that you presented in the?
Yeah, so I think I can share with you that.
Yeah, I was just thinking whether this select cave enabling mechanism can be used in a more, let's say, dynamic task. But I think in this case, your movements are quite slow with respect to arm or something like that.
Where is that? I should have that somewhere. Sorry about that. Let me, yeah. Sorry about that. Let me just quickly find the.
Thank you for your answer.
If there's other question, I can answer while I look for our paper. So.
Next is Camilo.
Yes, here am I. Hello, Mr. Cho, and thank you for the inspiring presentation. I got a question about the Slack enabling mechanism tool. And you showed us a slide where we saw that a tendon of the mechanism can be actuated while the other one remains blocked. I would like to ask you, can you please make me an example of the magnitude of the force needed to block the tendon while the other one is being pulled? Do you need a great resistance?
Right. If you look at our RAM paper, there is a detailed data. I don't have the detailed data with me here, but it's pretty small.
It's pretty small.
Okay. Yeah, it doesn't have to be big because as long as you can overcome the friction, so the level of that force is equivalent to the friction. So if you just block it, even with a small force, it's going to adapt.
Oh, okay, this is interesting because I'm actually thinking that such kind of mechanism can be useful for my research, which is on a surgical device. And so you said that you were making your work public, and you're going to make it accessible on our website. So I would like to ask you, where can I find news about this publication and this website?
Yeah. If you come to our website, biorobotics.snu.ac.kr, we will probably announce it if we make that available.
Okay.
It's not going to happen that soon, but we are hoping maybe early next year we should be able to.
Okay. To do that. In the meanwhile, I can read the papers and maybe contact you for further information.
Right. So we actually saw that there is quite a need for this kind of Slack enabling actuator. So we're trying to make it available to other people as well.
Okay. Thank you so much. It was very interesting. Thank you for the answer.
Right, thank you.
Okay, thank you very much. So next is Kai Walker.
Yeah, hi. Thank you for the talk. It was really interesting. I had a question relating to the single channel EMG control. So was this related specifically to just power grips, or were you able to classify different movements using that single channel, or did you just focus on that one grip?
We focused just on the power grasp.
Okay.
Just the power grasp, not other grasps, because we found that the power grasps, quite a large force. We really didn't do research in order to find out the real reason behind why this works, but our guess is that there is a large force being applied in the muscle tendon junction when you're doing a power grasp. But for other grasp, it doesn't. In the EMG signal, you can barely see the signal. Other postures. So this is sort of a very unique, I think, a way of using an EMG. It's not general, as you know. Most EMG driven intention detection, you have to attach multiple, right? Attach multiple EMG, and then you detect many different many different types of grasps. But this one, you have just single EMG, and it's very robust. Even if you change your arm posture, you still can identify your power grasp. So this is somewhat, you can call it narrow because you can only do like power grasp. But since you can do it in a very robust manner, I think we thought it could be, very useful.
Yeah, that was the part that interested me. I was just curious if you maybe could recognize different groups. But yeah, thank you for that.
Not really. Yep.
Okay, thank you very much. So next is Franny Tsubetsuri. I cannot pronounce.
Thank you, Professor, for a very interesting presentation. You presented 3 intention methods in your work. One is the button and the camera, and then the EMG. I'm just curious, what do you think in terms of like intention detection approaches? Because I mean, you mentioned the limitations of the EMG, right? That you need to sort of calibrate every time, but also it changes with the posture, especially for your power exo glove power instance, right? If you're using, like firefighters are using it, they are going to sweat. So how does that sort of affect your ability to be able to detect the intention of the user in those different cases?
Right. So actually, right now that VideoNet approach is, I guess the limitation is you need a camera that actually looks at your arm, hand, and the object. So it's right now for grasping, but probably, hopefully, it can be extended into different object handling or many different intention detections. That's what we are thinking. Yeah.
And so for the exo power glove, did sweating sort of affect the performance of your user detection ability?
Sorry, what did you say again?
Like, did sweating affect your ability to get the intention of the user for your exo power glove? Because they are doing sort of intense work.
I see. Okay, did sweating affect? You mean our VideoNet or
the EMG? They were single channel EMG.
Oh, the EMG.
Yeah.
Well, that's a good question because sweating could affect the EMG signals, but as you know, when we do these experiments, we make sure those things didn't happen. But I don't know. Maybe it could have happened. I think you've seen our video, right? And we didn't really check whether there was a sweating occurring or not. So that's a good question. Maybe I should ask my student who actually did the experiment, but he never had mentioned about the sweating issue. But that's a good point. So my guess is if there was sweating and if we weren't able to get a robust EMG signal, that could have affected the results. That's my guess. But I guess it's going to depend on the level, because if there is sweating, the signals will deteriorate, but by how much would be the question. And we were not just using, we were actually using machine learning. Actually, we are using neural nets to detect it. We are not just using the raw value. So it could have been more robust to the sweating. Yeah, but we didn't really look into that. we just thought, it's robust to many different parameters. It could have included sweating or not, but we didn't really do a control parameter study on the sweating issue. I think it's an interesting question. Something that we should do.
I appreciate it.
So this is the paper that I talked about for the person who asked me about. This is the control of a Bowden cable actuation system with embedded BOA sensor for soft wearable robots. So if you see this paper, we look at the hysteresis and we provide a way to reduce this kind of hysteresis and also nonlinearity caused by. So if you're using a Bowden cable, the bending of this Bowden cable actually causes nonlinearity. So, but if you can actually estimate the bending angle using the BOA sensor, so what BOA sensor is, it's a mechanical sensor. It runs together with our tendon drive, and you can actually estimate the bending angle of the tendon sheath. So I didn't put this into our slide because it's too technical, but if you're interested in this like technical stuff, you can actually read this paper and you can see that we have many different experiments done about the hysteresis and then removing that hysteresis to estimate the real value.
For sure, looks very interesting. I will read it. Thank you very much.
Yep.
Thank you very much. So next it's event there Adams. So do you have a question?
Okay, so
I think there were you have one more question. So the question is put in the chat. So Adams, you are here.
Hello.
yes,
Okay.
hi.
Yes. Prof, thanks for the insightful presentation. It's very, very insightful. I want to find out whether the Exorex is commercialized.
Mm-hmm. Oh no, not really. So like I said, our ExoWrist, it was like a sort of a pilot project. Yes, and we only actually
Kindly to whether you
oh, I cannot hear you. Can you?
hello.
Yes.
Yes. So as you just answered that, of course, it's not commercialized now since it is a pilot project now. Secondly, on the experiment that you've person living with stroke, I want to find out whether you just tried the experiment of those persons with hemiplegia and what was the outcome. Thank you.
Oh, you mean for the ExoWrist?
Absolutely, yes, that's correct.
Yeah, we haven't done any kind of clinical experiment with the ExoWrist yet. So, I mean, the student who worked on the ExoWrist is now working on some different topic. He changed the topic, so it's waiting for a new student to actually work on. So we haven't done any clinical experiment or anything like that.
Thank you very much.
Right.
Okay, thank you very much, Professor Kyu Jin Cho.
All right, thank you.
So this is your talk is very, very impressive, and you have a great discussion. So thank you very much again for your talk.
All right, thank you very much, and have a nice workshop.
Oh, thank you very much.
All right, thank you.
Okay, we'd like to move